And the first speaker is Yair Minsky. He will speak on windows, cores, and skinning maps.
Thank you. So I want to thank the organizers for inviting me. It's really kind of an honor to be here to celebrate the 25th birthday of the IMS. I guess I was here, I came here first in '93, I think, so not quite 25 years ago, but a little while. And I learned a lot from everyone here, just from Misha and Jack and the various people who came through, and it's really been a wonderful experience in many ways to be associated with the Institute. I learned an important skill I learned that I wanted to make sure I recorded was that I learned how to make the following doodle. Right, so I think that I don't think I was allowed to work here without knowing how to make the doodle. So this won't come up in my talk, but I just wanted to point out that I know how to make that doodle. Anyway, but the mathematical atmosphere here has always been wonderful. The kind of free exchange of ideas and interest in learning from each other. Actually, one more thing. So one of the things I always liked here was that in addition to the dynamics seminar on Fridays, there's always been a dynamics learning seminar on Wednesdays. I don't know if the day's changed. And I like the name learning seminar because it's a good idea and it points out what's missing from other seminars. So that was always a good thing. Okay, so all right. So what I want to talk about today. Can people see this board? It's joint work with Jeff Brock and Ken Bromberg and the Canary. And what I want to talk about, it's kind of an old subject. It's almost an archaeological subject. It's about Thurston's skinning map. So I want to spend a little while telling you what the skinning map is if you don't already know, and explaining a little bit more that we have to say about it than was known before. The skinning map, it's a self-map of Tychmer space. And it comes up in Thurston's proof of hyperbolization of three manifolds. It has to do with, in the deformation theory of a hyperbolic three manifold, there's a natural Tychmer space, and the skinning map is part of a self-map of that Tychmer space that Thurston used in the gluing problem that he set up to take a hyperbolic structure on a manifold with boundary and convert it to a hyperbolic structure on a glued-up manifold where you attach the boundaries together. So to make that work, you need to find a certain fixed point of a map of Tychmer space, and this is where the skinning map comes in. So one actually might ask why one wants to study this, since it's such a, the hyperbolization theorem is already proven. So why would one think about this subject at this point? So I want to kind of point out a couple of motivating points. One is that the deformation space of hyperbolic structures on a three manifold, so let's just say of a three manifold, is still kind of mysterious in certain ways. In particular, the boundary. This should be familiar to people who know about this doodle. The boundary of the deformation space is topologically sort of intricate. It's not locally connected. So let me write as a keyword local connectivity. So it's not locally connected, for example, but there are points where it is locally connected, and one can study a little bit better some of this information by understanding the skinning map. And I don't know if I'll get to that point, but at least I want to say that one of the applications we have in mind involves studying the boundary of the deformation space of the three manifold. Another thing is just kind of better quantitative understanding. If you understand this skinning map better as a quantitative thing in a more explicit way, it leads to sort of more explicit geometric control of the three manifolds. And so beyond just the fact of Thurston's hyperbolization theorem, one also wants to be able to say things about hyperbolic structures on three manifolds, and this is one tool for doing that. Oops. And then another point, which is part of why this is a little archaeological, is there's some mystery, at least in my mind, about Thurston's original proof of some of the aspects of the machinery that the skinning map comes into. So not all of it, you may know, not all of it was written down and published. I think there are probably people in this room who know it a lot better than I do, but there are aspects here that remain mysterious to me, and we, the four of us, have thought about how to recover some of the what was kind of implicitly in Thurston's program and understand it a little bit better. So that's another reason to study this thing. And finally, it's just it's kind of cool. So it's a really beautiful construction. So those are my reasons for talking about the skinning map. So let me tell you a little bit about what this is. So what's the setting? The setting is we have a three manifold. So the M will be a compact, oriented. There's a lot of adjectives here. I want irreducible, atoroidal, with non-empty boundary, and I want the boundary not to have tori. So non-empty, this is very important, incompressible boundary. So I'll draw you a picture in a second. So some of this can be dispensed with. The oriented stuff is just because if I allow non-orientable manifolds, I'll surely say something wrong. So that's what that's for. The irreducible and atoroidal is what guarantees that we have a hyperbolic structure on the interior of M. The incompressible boundary is important for this discussion of the skinning map. That's kind of crucial. Having no tori in the boundary is just a convenience. One can make the discussion with tori in the boundary, then you have to allow certain cusps in the structure, and anyway, it just complicates the words. So that's the setup. Maybe one should have some pictures of what I'm talking about if you don't normally see such manifolds. So first of all, you could take a closed surface across the interval, okay, which my cartoon of this always looks like that. Okay, closed surface across the interval. You could take let's see, the rest of these aren't going to be very specific. You could take one more thing you could have in mind. You could take a surface with boundary across the interval, attached along the boundary across interval to something else. And so, for example, so you could sort of imagine it looks like this. So here's a surface with boundary across the interval. It has an annulus in its boundary, right? And then you could attach it to, you could here take some other manifold and then draw a very complicated curve in the boundary of that manifold and thicken it and attach these two annuli together. And that's another, and if you choose, you'll see later why I'm saying it this way. So imagine this is an extremely complicated picture and this is this kind of simple picture, and you attach them together along an annulus, and it'll typically satisfy these conditions. And maybe one more thing, just to sort of make sure we know we have a lot of examples. You could take the three-sphere minus some complicated embedding of a graph. So take this graph, embed it in a very knotted way in three space, take the complement of a regular neighborhood, and that's a three manifold with boundary of this type. Okay, so that's the manifold we might talk about. And then, so where does the skinning map come in? I want to talk about,
what are non-examples? Incompressible boundary, for example?
Yeah, so a manifold with compressible boundary is, for example, just a handle body. Just take a surface in space and the interior of the region it bounds. That's a manifold whose boundary is not incompressible. So incompressible means that the fundamental group of the boundary should inject in the fundamental group of the three manifold. So in this case, for example, this loop here, which is non-trivial on the surface, bounds a disk in the three manifold. Okay. And it's important that I have boundary because this whole discussion takes place on the boundary. Okay, so, and So what do we have here? So I want to think about hyperbolic structures on the interior of such a manifold. So let's give a name to the
You want your graph to be non-trivial, right? You don't want this to be an off.
Right. I want the graph to not be a circle. So at least. So this would produce a manifold whose boundary is a genus 2 surface, right? But actually, I should say the way I usually draw these manifolds isn't like this. It usually looks. My caricature of these manifolds usually looks like this. There's a surface which is the boundary, and then there's some stuff inside. That's the actual picture I have in my head. Okay, so given such a manifold, let's let Q of M denote the space of marked, I'll explain what this means, convex, co-compact hyperbolic structures on the interior of M. So what is a convex co-compact hyperbolic structure? So it's the following data. So you need a group acting, so a group in PSL2C, which is discrete, and it acts. So such a group acts on H3 union the Riemann sphere, the ball, and in the Riemann sphere it decomposes into an open set, an invariant open set, and an invariant closed set called the limit set, and the domain of discontinuity. So this should be familiar to, I guess, everyone from either dynamics or geometry. So the action on H3 is discrete. The action on omega is discrete. It's properly discontinuous. And so there's a quotient manifold. We'll call it n sub gamma, which is H3 union, actually put a bar on it to close it, union omega modulo gamma. So that's a 3 manifold. And what I need for this to be convex co-compact is for this manifold to be compact. And then finally, the connection to M is that this is the data of the manifold. And then I said it was a marked structure. So the marking is this. I need a homotopy class of, say, homeomorphisms. I guess I should, maybe to be careful, I should say orientation preserving homeomorphisms from M to N bar. Okay? So I'm identifying M with this quotient manifold, which consists of a hyperbolic 3 manifold with a shell at infinity, which is this conformal surface omega mod gamma. Everybody okay with this so far? So another way of describing this is instead of writing it this way, you could talk about the convex hull of lambda, which is a submanifold of H3, and you could take the quotient of the convex hull of lambda, and that would be also a compact manifold, which can be identified with M, except in some degenerate cases where it would become so an epsilon neighborhood of that would be this. But I kind of want to focus on the domain of discontinuity, so that's why I'm writing it this way. So this says that convex thing has a compact quotient. Okay, so that's the set that we want to look at. But actually, it's inside a larger thing. So so QM is naturally part of what you might call AH of M, which itself is inside the character variety of the fundamental group of M. So what is this? This is just the discrete faithful representations, rho from pi 1M to PSL2C. Up to conjugacy. Okay, so it's not hard to see that once you have this data, you can this identification on the level of fundamental group gives a representation from pi 1 of M whose image is gamma. It's an isomorphism, so a discrete faithful representation. And then if you conjugate gamma in PSL2C, you don't change the hyperbolic metric. I should have maybe said that I don't care about gamma except up to conjugation, because the metric on M, on the interior of M, is the same. Okay, so this is part of the so this is in the space of representations. It's a natural. It lives in a natural way inside this variety of all characters on the fundamental group. Okay, and in fact, it's the study of this thing in here, which is one thinks of as the deformation theory of M. And this thing, in fact, it's a theorem of a number of people, many of them, actually maybe not in this room, but could have been in this room, that this is actually the interior of this. Well, actually, that's not true. Let me say this correctly. It's a component. This is a component of the interior of this. A lot of things go in here. The fact that here I just have representations of the fundamental group means that the homeomorphism type of the quotients I get here is not tied down. It doesn't have to be M. It could be something homotopy equivalent to M. So there are various technical issues about what goes on in here, but this is a particularly nice subset, and it's a theorem of due to Alfors and Baers. This is the Tychmer theory part. And actually, one should include, maybe for this level of generality, it just comes from their work, but I think, no, maybe not. So Marden, Maskett, and Craw, that this set, Q of M, can be identified with the Tychmer space of the boundary of M. Okay? So, right. I should have drawn you a picture. So let me draw you a picture of what this group gamma looks like. So a typical example here is that the limit set is some kind of collection of quasi-circles, an infinite collection of quasi-circles, whose the union of these disks is dense. Say, this is the limit set. And then the domain of discontinuity is this union of open disks in here, and the group acts on this. And you get each of these disks, modulo its stabilizer gives you a boundary, a conformal structure on the boundary of M. And this theorem says that you can deform the conformal structure of these things however you like in the Tychmer space of that surface, and you can always realize that deformation by a different representation as a Mobius group of M, of the fundamental group of M. Okay, so this is kind of, in some sense, the seminal theorem in this field. Okay, so that's the setup. And now I need to tell you about the skinning map. So in particular, a special case of this is when M is S cross R, S cross 0, 1, say, a surface group where the genus of S is at least 2. And then what do we get here? So Q of S cross 0, 1, which maybe for brevity I'll also call that Q of S, can be identified with the Tychmer space of S cross another copy of the Tychmer space of S, with the opposite orientation, because the boundary of this is 2 copies of S. Okay, so that's what a conformal structure on 2 copies of S would be. It's just 2 conformal structures. And this is the original Baers simultaneous uniformization theorem, said that for any 2 conformal structures on S, you can build this picture with a sort of single, now it's a single quasi-circle separating 2 domains, and one of them gives you one structure and the other one gives you the other structure. So this is the quasi-Fuchsian group. Okay, so finally, the relationship between this and the skinning map is the following. If you consider the inclusion of the boundary of M into M, okay, it induces a map from Q of M to Q of the boundary of M in the following way. So this map goes the other way, right? So you can think of this map as being induced by restriction of the representations. In other words, it's a little easier to think about if the boundary of M is connected, then it's just, when you have this inclusion, you also have the fundamental group at the boundary, which injects into the fundamental group of M. And now if you have a representation of this fundamental group, then you can restrict it to the image of the boundary group, and you get a representation of this group. And so that takes you from structures on M to structures associated to the boundary of M. I'm already cheating you a little bit. I don't know who caught that or not. So really, so what I just said tells you that there's a map from here to discrete faithful representations associated to the boundary of M. But in fact, the image lies in the convex cocompact locus. This is not a trivial. It's an actual theorem due to Thurston that's where the image lies. So we have this map, and a little bit more carefully, what does this look like? So this is the Tychmer space of the boundary of M, and we have a map to two copies of the Tychmer space of the boundary of M. That's what this guy is. And so what does this map look like? So if you put a structure on the boundary of M, where does it go? It should go to a pair of structures. And the pair of structures look like this. One of them is just a copy of X itself. And the other one is something else. So we'll give the other thing a name. We'll call that sigma of X. So that map, actually, yeah, there's a bar. There should be a bar here and a bar there, I think. So I want this to be a holomorphic map. I should be careful with the bars. All right. So this map is the skinning map. So sigma or sigma M is the skinning map. Okay. And I think I owe you a picture of how to think about this as a geometer. So let me draw the two relevant pictures. So picture number one is what's going on with the manifolds that we have. So I had this kind of caricature of the manifold with boundary, and if you, let me draw that here. So let's draw this. If I have some manifold with boundary, now you should think of, actually, this is just, so there's some complicated stuff in here, and then I really want to, there's kind of an end to the hyperbolic part is non-compact. It goes on forever. This is like a product, surface cross R. And at infinity, there's a structure, a conformal structure on this surface, which is sort of obtained as the limit of the hyperbolic structures on level subsurfaces. And we'll call that X, okay? And so that's the Alfors-Behr's theorem tells us that X actually uniquely determines the metric inside. It's kind of an abstract theorem. And then when this inclusion of the boundary gives rise to a restriction of representations, and on the level of manifolds, it gives rise to a covering map. So you can think of a covering map associated to the surface, and the covering manifold looks like this. It has to be, whoops, I ran out of space, but this is the manifold that lives in Q of boundary M. So it's a hyperbolic structure on boundary M cross R. On one side, I get just a homeomorphic lift of this end. The covering map will just be a homeomorphism on this part. So I get X exactly on this side. And on the other side, I don't know what I get. That's the thing I call sigma of X. Okay? And so it's what I get by unwrapping everything in here and then looking out at infinity and seeing what I see. That's what this is. So Thurston's name, the skinning map, has to do with the idea that you peel off the skin on this side and then you look inside and this is what you see. So the other picture one should have in mind is that if you look on the universal cover, and in particular at infinity, you have the picture I drew before with all the, let me draw one of the domains. And then there's all the other domains. And I should actually, before I drew them all disjointly from each other, and actually the case I want to talk about today is one in which these are allowed to touch. So maybe I'll draw maybe a more correct picture. So there's all these disks which are allowed to touch. Anyway, I'm not going to be too careful about this, but there's some thing like this. That's the kind of given X. So actually, you could think of it this way. You could lift the structure on X lifts to the structure on one of these blobs, and actually on all of the blobs. So every one of these is a translate of the first one by the group. So somehow. The conformal structure of X is lifted separately to each of these things, and the whole thing is invariant by the action of the group. And then how do I get this guy? Well, what I do is I look at this thing with just the stabilizer of this component. So let's say, say gamma naught is the stabilizer of this component omega naught. And it's isomorphic to the fundamental group of the boundary. So it just acts on this one, and it. Yeah, for this picture, the boundary only has one component. If I had several components to the boundary, maybe I could color them different colors, and then these domains would get colored by different colors. And then there would be orbits of the group that preserve the coloring. And then what would be going on here is that this Tychmer space would be a product of Tychmer spaces. So this X would actually correspond to an assignment of several conformal structures. Yeah.
Are you in the quasi-Fuchsian case, or are you?
No. I'm purposely not in the quasi-Fuchsian case. I could tell you the quasi-Fuchsian version of the skinning map. That's a good, it's important case, but.
The Bayes theorem is the quasi-Fuchsian theorem. So
The Bayes theorem on this line is the quasi-Fuchsian theorem, and here it's the general theorem.
But how did you get to two copies of Tychmer spaces within?
Yeah, so first of all, I was kind of implicitly hoping you would think about the case where the boundary of M is connected. And then I get two copies because Q of the boundary of M is the quasi-Fuchsian representation of the boundary of M. So they have two sides. So it's really boundary of M across the interval. So I get two copies. So that's where the two copies come from. But I'm saying that one of the copies is just identical to where I started, and in the other one it's interesting. So, and then in the case where there are several boundary components to M itself, it's the same formalism, but now each of these represents itself an element in a product of Tychmer. Okay, so right. So what happened in this picture is that when I act on this picture by just the stabilizer of this component, then I also stabilize its complement, which contains all the other components. And so let's call that complement omega 0 C maybe. And omega 0 C modulo the stabilizer of omega 0 is another copy of the same surface. But in this copy, I don't get X, I get all that stuff on the other side, which kind of looks like a bunch of regions. Actually, maybe some of them are more complicated regions. But there's some kind of infinite picture with pictures of the limit set in it, all kind of scrambled inside here. And it's this. This is what Thurston called the Leopard spots picture. So there's some kind of aggregate conformal structure that's pieced together out of all of this information. And that's the skinning image of X. Okay? Everybody happy? So, okay. So
the one thing I'm not happy about is the line that you put over sigma of X.
Yeah, I probably got it wrong. Let's see. So I want to think of, I might have it wrong. So let's see.
Sigma of X really is in that conjugate Tychmer space.
So then sigma is anti-holomorphic?
No, sigma is holomorphic. It's a holomorphic map to that product of Tychmer spaces.
Oh, you may be right. I'm happy to erase this bar. It doesn't make me happy anyway to erase the bar.
If you put the bar there, you can, but then it's an anti-holomorphic.
Then it's anti-holomorphic.
To the product of twice the same Tychmer space.
Right. Okay. I was trying to avoid anti-holomorphic things by putting the bar on. Clearly, I outsmarted myself.
Yeah.
You already have a bar on the boundary, yeah.
Yeah, the bar on
Right.
the M is right. But that's not anti-holomorphic. That's just a different Tychmer space.
Yes.
Perfectly respectable other Tychmer space.
With the surfaces. Okay. All right. I'm happy with that. Okay. Right. So what are we going to do with this map? So I was going to say, I'm going to actually maybe commit a sin and not tell you about the gluing problem that Thurston solved with this map. I just want to tell you a little bit about the map. So So facts about this map. So first of all, the map is strictly contracting. And let me be careful about this. Strictly contracting. Thurston proved that it was pointwise strictly contracting, so not with a uniform contraction. So its derivative, the norm of its derivative is less than 1 at every point, but it's not necessarily bounded away from 1. McMullen later proved that in the acylindrical case, it is bounded away from 1. But I'm actually interested in, you'll see in a minute, in the general case, and there I think this is the best you can do. So this is a pointwise statement. I won't come back much to this statement, but the other theorem that Thurston proved was the following, that if M is acylindrical, I'll say what this is, then the image of the skinning map is bounded. So you have this Tychmer space as an open manifold, and the map, the skinning map, has a bounded image. This is known as the bounded image theorem. So what is acylindrical? So what's a cylinder? A cylinder is an essential map, is an essential homotopy between circles in the boundary of M. So the kind of the most cylindrical manifold you could have is a product. If you take a product of a surface with an interval, then any curve on one side can be homotoped to a curve on the other side. That's an essential cylinder. So this thing is nothing but cylinders. And I should say that in this case, this theorem, this is certainly not true. And actually, this is not true either. So here, you have to say if M is not a product or an I bundle. So except in that one case, this map is contracting. What happens to the map in the case of a product? Well, in fact, if you think about it, if you have so X, the structure X on the boundary now is two things, X1 and X2, and the skinning map takes X1 and X2. Well, so if you think about what happened, now you'll have to correct me if I'm doing this wrong. I'm sure I'll do it wrong. So I think it should be this, right? But I'm going to get the bars wrong. But have I got the bars right? Yeah, because I had to flip the orientations. But okay, so if I have a structure on the bottom and the top, and then if I look from the top, what do I see on the other side? I see the bottom with the opposite orientation. So and vice versa. So the skinning map now just interchanges the coordinates, and it's an isometry, and it does not have bounded image. It is surjective. So that's the most cylindrical case looks like that, and I should say that this is why Thurston's hyperbolization theorem for manifolds at fiber over the circle required a different proof, because this whole skinning discussion doesn't quite tell you what you need to know in order to perform a gluing on such a manifold. Okay, so the last thing I want to say for the moment about the gluing discussion is that when you have a map which is both contracting and has bounded image, then it must in fact have a unique fixed point. And if you combine this information with the gluing data that might glue two manifolds together or glue a manifold to itself by identifying its boundary components, you end up with in order to produce a hyperbolic structure on the glued up manifold, you need to solve a certain fixed point problem which involves this map sigma. And so this is what you need in order to solve that fixed point problem. Okay, so that's the original reason why this map comes up. Okay, so I should tell you what it is that we're trying to do with this. And I will, the time I have, I'll try to give a feeling for what it is one has to do to prove the second theorem, the bounded image theorem. I'm going to ignore the first theorem for the rest of the talk. That's just for background, and it's number 2 that I really want to think about. So what happens in the cylindrical case? And in fact, the theorem I want to talk about is a kind of relative version of that bounded image theorem, which holds in the cylindrical case. So we already described the most cylindrical case. There's nothing much to say, but the kind of generic situation is the following. So there are cylinders in the manifold, and there are places in the manifold where there aren't cylinders. And the way that one understands this is via what's called the characteristic submanifold. So let me give you a 1-minute description of the characteristic submanifold. So this is also known as part of the JSJ decomposition of a three-manifold. So the J and S and J are Johansson, Shalin, and Jaco, or maybe it's Jaco, Shalin, Johansson. I don't. Actually, it probably should be, maybe the right way to write this is Jaco, Shalin, and Johansson. So, so what is a characteristic submanifold? It's a submanifold of M, which is a union of I bundles. So an I bundle is just a surface cross interval, or there's a twisted version where it's an unoriented I bundle. So I bundles and solid tori inside M, which so they're attached to the rest of M along the obvious annuli, well, not the obvious, certain annuli, such that M, such that all essential cylinders or annuli, I guess people call them both, in M are homotopic into this submanifold. Okay? So, and it's unique up to isotopy. So this is kind of a canonical object inside the three-manifold. So in the cartoons that I drew in the beginning, for what kind of three-manifolds you might have, there was one, maybe it's gone now. So I encourage you to think about a case about a surface cross interval attached to something else. So there's another cartoon of the same thing is, so surface cross interval, so this is F, attached along, well, how am I going to draw this? So along this annulus to maybe something complicated. So maybe this manifold, it has some boundary, but there's some kind of topological obstruction here. There's no curve on the boundary here that is isotopic, that is homotopic into anywhere else in the boundary, except for the curve here, which is just part of this. Okay, so that's an example. In this supposed picture, this is sigma of M. Another kind of picture that you might have in mind is you might imagine, let me draw this kind of in profile. You might imagine several pieces that are acylindrical that are attached along a solid torus. So imagine that the local picture you should imagine here is there's a disk across a circle, and then these guys are annuli attached, and complicated things are attached along this in some number. Okay, so that's another example. So here's sigma of M. Here is this solid torus. Okay, and then and the idea is supposed to be that stuff in here can degenerate. That you don't. The skinning map is not controlled on this part, but it should somehow be controlled on this part. That's the theorem I want to state. So so let's let I don't know what to call this. So maybe this is called the non-window boundary of M. So Thurston called this part the window because you could imagine that if this whole manifold is made of glass and you looked on this side, you would see no distortion going through. So that's the window. And over here, you get a sort of a mess. So the non-window part is just the boundary of M minus the boundary of the characteristic submanifold. And let's see. So for example, in this picture, it would be this part, whatever it is, but you would throw away this. I think that's right. I think there's actually a little bit more. I think actually there's something. We should maybe keep an annulus for the solid torus as well. So in the way that I'm going to state this, I will probably be lying to you about annulus components of this surface, because you have to tweak the statement a little bit. But so just imagine you have a complicated surface over here which has no cylinders in it. So that's what this is supposed to be. And then one way to state the theorem is the following. It says if you look at this subsurface, there's again the same kind of restriction map as before. It gives you, except on the level of surfaces, gives you a map from the Tychmer space of the boundary of M to, let's call it the Fricka space of this subsurface of the boundary. So what is this? This is hyperbolic structures of manifolds with boundary, which allow boundary. So if I have a surface and a subsurface over here, then a hyperbolic structure on the surface gives me a hyperbolic structure on the surface with boundary. And you can think of that as a hyperbolic structure on the cover associated to the subsurface. So there's like an extra, again, it's a similar unwrapping picture. And so this lifts to a hyperbolic structure here. That gives you this map between this Tychmer space and this Tychmer space, which allows you to basically ignore what's outside, what's outside of the surface. And now the theorem is that if you look at the composition, so take the Tychmer space of the boundary and compose it, let's call this map R. So you take sigma, which maps you to the Tychmer space of the boundary bar, and then I do this R, I guess now maybe I have to reverse orientation. Okay, this composed map has bounded image. Okay? So another way to say that is, so what exactly did we do over here? Let me sort of point to this picture. We put, in this setting, we put a conformal structure on the top and on the bottom. Okay? Any conformal structure on the top and on the bottom, and we look at the hyperbolic structure we get, and we restrict attention maybe to this part, and we lift to this boundary component, and we look inside, and we see out at infinity below us the skinning data, the image of the skinning map, and what this theorem says is that everything in this subsurface down below is bounded. Now it can't degenerate in the Tychmer space. Over here, if we look down, we'll see, roughly speaking, whatever data we put on the other side. And that could have been anything. So we can't expect the skinning image on this side to be controlled. But this theorem says that on this side, we have control. Okay? That's the theorem. What?
What exactly is M? M actually the whole thing, including the left and right?
Yes. M is the whole thing, and and this decomposition comes from the JSJ theory. So the decomposition tells me which parts I can control. But M is the whole thing.
Part.
Say again?
All cylindrical parts have the same theorem as.
If there were no cylindrical part, then I would have the same theorem as.
But the cylindrical part somehow remove it.
Right. So the trouble here. So there is a. I'll say in a second. There is a kind of Thurston proved a compactness theorem for the acylindrical part, but it's not quite this statement, and the difference is a little subtle. So let me. And let me say the. Yeah, I don't. Yeah, I guess I'm at that point where I have less time than I thought I would have. But so let me first. So let me say two more theorems of Thurston, which give us an idea of how how he proved the bounded image theorem and how we are proposing to prove this relative theorem. So Thurston proved that first of all, if M is acylindrical, that's the original setting, then AH of M is compact. Okay, so you look in the space of representations into PSL2C, you get a compact set. Okay, so the discrete faithful representations form a compact set. And then the relative version of this theorem is that, so if in general, so I guess it's like part 2 of the same theorem if you want, AH of M minus the this part, it's actually, I could state this a little more carefully. The solid tori are going to trip me up. The solid tori are also controlled, but let me just write it this way. If I throw away the cylindrical part, this is also compact. Okay? So that kind of looks like what I'm trying to say here, right? Here I'm saying that I have boundedness on the on exactly the kind of complement of the cylindrical part. And here Thurston is telling me that I have a compactness theorem for representations on the complement of the cylindrical part. So why isn't this just sort of all obvious? So let me give you a cartoon proof of the bounded image theorem and try to indicate what's difficult. So proof of the bounded image theorem. So what do you have to do? Suppose you have a sequence xn in Q of m. Okay, so that translate, or rather in the Tychmer space, of the boundary of m, which are therefore by the Alfors-Bayes theory associated to a sequence of representations in Q of m. Okay, and this is inside AH of m, which is compact. So you could take a convergence subsequence. So you can assume that rho n converge as representations to some limiting representation.
So that AA is compact?
So I'm using, this is in case 1, in the acylindrical case. So AH of m is compact by this theorem. So this sequence of representations has a convergent subsequence. So I look at that convergent subsequence, I get a new hyperbolic structure on m. It's not in Q of m necessarily. So I have to study those sorts of representations, and then, in fact, one has to prove. One has to prove something already here, which is that that the skinning image of rho is well defined. That there is so this guy is not convex co-compact, but if you look inside, you will see conformally finite ends. Okay, so you need to prove that theorem, which is what Thurston did in this acylindrical case. What? Tychmer boundary end. Thank you. Okay.
Bar.
What? With the bar. Good. I should just draw a bunch of bars over here, and we put them in as we need them. Okay. So I have this conformal structure for the limiting thing, and then I needed to prove that these guys had bounded image. So then the sigma m of xn, the skinning images of the sequence, should converge to this limiting guy, and therefore they're bounded. Okay? So that's kind of the proof, except this arrow is a little bit difficult. So it's not true in general. I should say, what have I done? This I'm kind of saying that I can extend sigma m to a map from all of AH of m to the Tychmer space of the boundary. Okay, this is what I'm trying to do. And it should be continuous. Okay? This is what I need for this proof to work, because I need this convergence to work. And the map that associates representation with the conformal data at infinity is not continuous. Okay, so maybe, so I didn't,
So you have a few minutes. So.
Okay, so I have 5 minutes, and then I'll take another 5 minutes after that, so then I have, okay. Okay, so, right, so this is the kind of outline of the proof, but the proof forces you to deal with this issue that you can't just say that this map is automatically continuous. Okay, that's already a problem in the acylindrical case. And in fact, let me give you, if nothing else, one should have the following picture in mind from this talk. There's kind of a long study of this, originating, I think, with Kerckhoff-Thurston, and kind of fully analyzed by Anderson Canary and McMullen, and there's other names I think I should put here. But the main observation, this kind of non-continuity effects that happen with limits, maybe the clearest description maybe is this one. So let me give you an example, a sort of quick example. So take the following manifold. Take, this is now a sketch. So take, this manifold is S cross an interval minus a neighborhood of a level curve. So a regular neighborhood of, say, some curve gamma cross a half. Okay, so this is meant to be a curve in the middle of the surface. I've deleted it from the manifold. So this has a torus boundary, so it's not in our setting. But still, it has a hyperbolic structure. And in fact, its structure is controlled by conformal data on the two boundary components. So if I put conformal structure, say x on this side and y on this side, that determines a hyperbolic structure on this with a cusp. Okay? So think about that example for a second. In that example, put in a surface. I'm going to give you two copies of a surface, of the surface S in here. One of them is just this one. Think of this as an embedded copy of S. I'll explain what's going on in a second. And then I want to produce a sequence out of this using Dane filling. So for those who haven't seen Dane filling, this is going to be a little bit telegraphic. But you can perturb this hyperbolic structure so that this cusp becomes a solid torus with a geodesic core, and the surgery coefficient associated with the solid torus being glued in here can be made as large as you want, which means that, and moreover, if you do it with an integer surgery coefficient, when you glue in the solid torus, this will still be a surface cross I. So if this is kind of, if you call this one M infinity, then there's sort of an Mn, which just looks like you've sort of filled this in, and you get a conformal. You get it sort of you get a quasi-Fuchsian manifold here, and if you think about this representation of S into this picture, that gives you this S over here, and the data, the quasi-Fuchsian Tychmer data that describes this manifold is then an X on this side and a twisted, so tau to the nx, which is a Dane twist on x, which represents the cost of pushing this surface from this side to this side. It has to go through this solid torus, and because of the surgery coefficient, it gets twisted around gamma. And so this is the Dane twist. So I have a sequence of conformal structures which converges to this manifold geometrically.
Wait, what was the dependence on n? What did you say?
Dependence on n is that I've put in, I've done an n Dane surgery here. So I've replaced the curve which bounds a disk in this solid torus is a curve that goes once around in the vertical direction and n times around in the surface. So that when I do that, then a homotopy through that solid torus from top to bottom costs me exactly n Dane twists on gamma. So I still get a surface cross R, but the marking has changed from top to bottom. So what I'm saying here is that, okay, so this is sort of, so if I have this sequence of representations, so this is now an AH of the surface S. So first of all, the manifolds converge geometrically to something new, but the representations of these copies of the surface in here converge to a cover of this manifold. Let me sort of say actually. So these guys converge as representations in AH of S. To let me draw it as a cartoon. It's still got x on the top, but there's a parabolic cusp on the bottom associated to this gamma here. If you look at this copy of gamma, it sees the cusp, and so therefore in the cover associated to this surface, I have a cusp. So all right, so this is converged, but down below I've got something with a cusp in it. Okay, well that looks like some kind of reasonable behavior, but here's a weirder behavior. If I replace this S with a surface that wraps once around the solid torus, once around the cusp, then if you think about what happened, it turns out that now when I fill in the solid torus and then I ask, what do I have here? So I'm going to just have to ask you to believe this. Now the structure that I see on the top of the surface is no longer x. I think it's, if I have it correctly, it's tau to the n x on this side and tau to the 2n x on that side. I might have this backwards. It converges, however. What does it converge to? It converges to this picture, and in this picture I have this copy of the surface which is not homotopic to the other one because there's a cusp in the way, when I take the cover associated to this thing, I will get a new structure where there's still a cusp on the bottom, but on the top there's a different conformal structure, which arises from some weird cover here that sees more than just x. And I'm not going to get into why that happens. But what's the point? The point is, so here I have a sequence of representations so that the limit on the top component doesn't have any cusps. It did not go to infinity in Tychmer space. It's a finite point in the Tychmer space. But the data here and here went to infinity. Okay, so it is not true that I can kind of, well, so so a certain continuity property here is not working, right? I cannot conclude from the fact that these went to infinity does not imply that, or rather, the fact that this was a point in the interior of Tychmer space does not imply boundedness for the sequence. Okay, this is kind of an issue of, this is the problem, and now I'm really running out of time, but I want to point out that the thing that went wrong, the thing that's going on here that's causing the trouble is a combination of two things. First of all, yeah, it's actually not proper, right? It's not. I said not continuous, but it's not quite what I wanted. There are discontinuities too, but the main point here is that it's not proper. Yeah, you're right. So, actually, maybe I'll draw this here. So, the issue it's a combination of 2 points. One is that one is the difference between algebraic and geometric limits. And the second, so in this example, I had a convergent sequence of representations. That's called an algebraic limit because it's sitting in its representation variety. But I also had a sequence, if you look at what happened here, the groups themselves had a geometric limit, which was a bigger group. This group here is a bigger group into which the original surface group embeds as a subgroup. So the geometric limit is a bigger group, and equivalently, the algebraic limit manifold. So there's an algebraic limit manifold which is associated to the limit representation, and it covers the geometric limit manifold, which is the Gromov-Hausdorff limit of the sequence of manifolds. Okay. So the first point is that these are not the same. That's one issue, and the other issue, in fact, dramatically not the same. It's possible, for example, for this one to have infinitely generated fundamental group, whereas this one is the same group as before. And the second thing that's a little more subtle is that there's a lack of embedding. So what happened here in this example is that the algebraic limit, if you took a core surface, a cross-sectional surface for the algebraic limit, and you tried to map it into the geometric limit, it immerses, but it does not embed, and it is not homotopic to an embedding. Because I've wrapped that surface around the torus. And that turns out to be the crux of the matter. So if you could embed the compact core of the algebraic limit inside the geometric limit, then you could sort of understand which end is above you and which end is below you, and you can control the conformal structures. That's kind of the very brief, the 1-minute lesson. So in fact, one way to prove this theorem, even in the acylindrical case, is to be careful about to show that when you have an acylindrical manifold, then the algebraic limit of a sequence has a core, a compact submanifold, which embeds in the geometric limit, and you can use that to control the skinning image. And then the last thing to say about this is that in the general case, we don't. So in general, we don't even have algebraic convergence, right, of the whole thing. So I'm skipping on a lot of details here. I apologize, but if you had this kind of I-bundle piece and then an acylindrical piece, then you know that the representation converges here, but you don't know anything about this. And in fact, what will be happening is that they'll be pulling. You could have a sequence of structures in which these are pulling apart. You could imagine that there's somehow, the curve here, the core of this annulus is getting shorter and shorter and somehow this part is converging, and then somehow over here, this is getting farther and farther away. In between them, there's a huge regular neighborhood of this geodesic, which, and in the limit, somehow this converges to a cusp, and the distance between the two sides goes to infinity, and you get a bunch, and the thing falls apart into a bunch of separate limits. And so you don't have any chance to build, one object in the limit which it embeds. However, you can replace it with it. So there's kind of, so what we have to produce is kind of, I don't know what to call them, maybe relatively uniform cores. So you piece together, you have to look at all the algebraic limits of all the pieces, and different pieces converge independently to various things. You have to now piece them together and build in your sequence of manifolds a sequence of controlled subsets, which are topological cores of the manifold, which means they carry the fundamental group. They're embedded, and you control the parts of them that you want to control. And once you've done that, then that's sort of the first step to getting from that internal data to the conformal data at infinity. And So there's additional machinery you then need to connect yourself from, once you have some controlled object in the interior of the manifold, you need to sort of look below it toward the skinning image at infinity, and you have to explain when you can control what happens. There's still an infinite amount of room between you and infinity, and you have to explain what happens there. But that's maybe enough, so I'll stop.
Any questions or comments?
Yeah.
So when you stated this point too, the acylindrical case, you alluded to a fixed point type statement. So what does it mean? If sigma of x is just x bar itself, so what's special about that?
If sigma of x, if you actually have a fixed point. Yeah. So in the that's a great question. In the acylindrical case, if sigma of x is x bar, that allows you to glue the boundary to itself by the identity map. And so what you will get is a hyperbolic structure on the double of the manifold. So this is how you prove. Yeah. So if M is so there's a kind of so there's a theorem that comes out of this that says that if M is acylindrical, that means that the double of M is hyperbolic, because you can just glue using the identity map. And then, using mass-star rigidity, if the double of M is hyperbolic, then the map of the double of M that interchanges the sides is an isometry, which means that the boundary of M inside the double of M is totally geodesic. So what this really means, so what you get out of this is, so Kurt McMullen actually wrote about this in his paper on the skinning map. So Kurt's contribution to the whole story is significant. But so he showed so that's what happens from the skinning map in this case. If it's acylindrical, you have the structure on M with totally geodesic boundary, which means that the pictures that I've been drawing can be straightened out to be circles, actual round circles. And so all of these acylindrical manifolds have structures, and they're unique with this sort of picture. But in general, what you need is you have some other gluing map, and that map has to have a fixed point. So usually, the usual setting is you have M, and you have some involution tau from the boundary of M to the boundary of M. So think about it as gluing two components of the boundary, and you need a fixed point, not of sigma, but of tau composed of sigma. This is the thing that you actually need a fixed point for. So in this case, tau is the identity, and so.
Yeah.
Another question?
So, because you don't have any more time, let me ask you a question. Why one should expect the skinny image to be bounded? I mean, in 5 seconds or so.
Wow. You mean, yeah, why should I expect to be bounded? I mean, I think, how did Thurston come? I don't know. I mean, now it's sort of part of the furniture. I sort of am used to it. But I mean, this compactness theorem is one reason to expect. The compactness theorem for representations leads you to that, right? So I didn't say anything about the proof of the compactness theorem. So maybe, let me say not Thurston's proof, but the proof that came afterwards of Morgan Shalin and sort of later refinements of that. If you have an acylindrical manifold and you have a sequence of representations, if they don't converge, then something is blowing up somewhere. And then the way we now think about this kind of thing is you can take hyperbolic space and rescale it, and you get an R tree in the limit. So now you get in the limit a representation of the group on an R tree. And if a group acts on an R tree, it's a special kind of action. It's called a small action. We talked about this yesterday. So then this action forces the group itself to split along something. And that corresponds to having a cylinder. So the actions on trees correspond to splittings. And that's kind of so there's this theory that says when can groups act on R trees in this way, and they can't do it if they don't split along cyclic subgroups. So that's one explanation. Maybe John has a better explanation.
Try to imagine deforming the complex structure in one of the spots on your Riemann surface.
Yeah.
We know how to do that efficiently. Efficiently means you put an invariant quadratic differential in that spot, right? And you put ellipses that are aligned with this quadratic differential.
And that's why leopard spot.
Yeah.
So the leopard spots, right? So each leopard spot has a kind of its own group and its own invariant ellipse field that describes the deformation, right?
Now you start thinking about what you pull back this Beltrami form, all of the other spots.
Yes.
And you start thinking, how much can that look like something coming from a single quadratic differential on the whole surface? Right. Well, it looks completely different. It looks totally disorganized with ellipses going every which way. That's why it's contracting.
That's why it's contracting, right? So this is Bill's proof that it's contracting. Exactly this, right? And Kurt had this refinement of that argument in which he proved that it's strictly contracting by studying very carefully the sort of using non-amenability of each stabilizer on a spot, right? So he showed that you can actually definitely make it more efficient. But it doesn't quite. I would love to know a proof of the bounded image theorem that operates entirely on the formal boundary. I mean, I've actually tried. I spent a few unproductive hours thinking about that. Like if you had this pattern of spots and you were allowed to do whatever you wanted to a spot, can you argue that still the overall structure can only move a bounded amount? And I don't know how to do that.
Way sentence, I didn't get it. So what is the every which ways, that he said, what does that prove?
That proves that the map is contracting, but it doesn't prove that it has bounded image. The point is that suppose you deform the x side, the original side, and on the other side, in the skinning image, you get the lift of that deformation to all of these spots. That lift looks like it's some measurable field of ellipses that's invariant by a group. In particular, it has infinitely many zeros. Right? The quadratic differential that you lifted up here has infinitely many zeros. On the other hand, you know that the best map from your original structure to the new structure is a Tychmer map. And a Tychmer map has finitely many singularities. So this is obviously, except in a trivial case where you have a product manifold, this is not an optimal map. And therefore, in fact, the map is, therefore, you're actually closer than you think you are.
You typically have fractal boundaries to all these spots, so that's not going to be compatible with having a Tychmer foliation either.
That's right. Yeah, there's sort of nothing, like John said, it looks nothing like a quadratic differential. That's the point. And that's where you get strict, the contraction at each point.
Now, there's a further thing to say. That on the level of the surface, you might have leopard spots, but you might also have zebra stripes.
Right. I tried to make one over here. That was supposed to be this one, right? I think.
And within the zebra stripe, it is possible to make that zebra stripe big and to have the ellipses actually look perfectly civilized in that part.
Right.
Which is that is what corresponds to cylindrical manifolds, that there are zebra stripes. And that is why we do not get uniform contraction. When there are any, when your manifold is cylindrical, because then there are zebra stripes, and it is possible to find quadratic differentials, which are essentially supported within the stripe, and where within them they are looking like a genuine quadratic difference.
Right. And that in my picture here, that corresponds to picking a curve on this side and making it short, very, very short on both sides, so you get an extremely high modulus annulus sitting on both sides, and then a deformation just in that annulus will look quite big from either side. Right? That's the
I think we are getting
yes, sorry.
all questions. There are so many beautiful questions and beautiful lecture, but maybe during coffee we ask. Thank you very much. And